Yeah, I have a question.
Go ahead.
How are you doing, by the way? So I just wanted to know, as far as action and reaction problems, where like how do you know which part of the problem has a negative and then which part doesn't? Do you know
Okay. So what you're asking is which is the action and which is the reaction?
Yes, I think so.
Okay. That's kind of like asking which one is the opposite sex. Okay. Well, pick one of the forces as an action, and then its reaction is in the opposite direction. Let me give you an example.
I got it. So doesn't really matter, I guess.
No, it doesn't matter. The
I end up with
action and reaction are just names. You can call either of them the action, then the other one is the reaction. They form a pair.
mm, okay.
So if we have a block sitting on the floor, let's call the action the normal force of the block on the floor. Well, then the reaction is the force of the floor on the block. And we use a negative sign for the downward and positive for the upward. That's just a convention. So the negative or positive sign comes from the coordinate system you choose. The each one of these pair is the opposite of its other is the opposite of the other. I'm running out of words to use. So you can consider either of these to be the action, the other one's the reaction. All right, I think that's clear.
Yeah, I got it. Thank you.
Okay, good. All right. Okay, any other questions? What about chapter 4 M and P or any of the pit problems from chapter 4?
Yeah, I had a question. For problem 4.5 on, I mean 4.54 for the MP problems, the letter D specifically. I wrote it down
Okay.
yeah, like yesterday or 2 days ago. I don't remember exactly why I had a question, but I'm sure it'll come up.
Okay, well let's look at it. So you have an 8 kilogram block sits on a level floor. You give the block a sharp push and it travels 8.22 meters in 2.8 seconds before coming to rest. You measure with a different push on the box and it travels 4.2 meters in 2 seconds. Do you think the box has a constant acceleration as it slows down? Explain your reasoning. Well, here's the box. You give it a push, and it has an initial speed v0. Now, what are the forces acting on this box? Well, let's do a free body diagram. On the box, I have gravity acting. On the box, I have the normal force of the floor acting. And once my hand is no longer contacting it, once I've done with the shove, there's no applied force. The only force is the force of friction. And the force of friction is going to oppose the motion. And we know from our model that the frictional force is equal to mu. Now, this is a kinetic mu. I'm just going to write mu times the normal force N, which is mu mg. The acceleration is the force over the mass. So that is mu times g. So from that reasoning, clearly the acceleration, which is actually negative in this case, is going to be a constant. It's mu times g with either a positive or a minus sign, depending on how you want to define your coordinate system. Okay, well, let's look at the data and see if we see that. Well, actually, no, I don't think that's what they want you to do. I think they want you to use the reasoning I just gave you for part A. Now, part B, add books to the box to increase its mass. Repeat the experiment. Okay. So the results, including the initial experiment with no added mass, are given to the table. In each case, did your push give the box the same initial speed? Well, probably not. So how do we determine what the initial speed is? Well, we know the acceleration is actually minus mu g, because that's in the negative direction.
Professor?
So v squared minus v naught squared equals 2a delta x. Well, we know that v is 0 because the box comes to rest. So we have minus v0 squared equals minus 2 mu g delta x. Now, from the data in the table, you can determine what v0 is. This is a minus v0, so there we go. Now you can determine what the initial v0 was. The average horizontal force F exerted on the box by the floor, the same, of course it is. Okay, so graph the magnitude of the force F versus the total mass M of the box plus its content. So how do you do that?
As far as the
Oh, I
friction,
see. Go ahead.
sorry, yeah. As far as the friction equation, that's like the mu times the n, or yeah, that equation. I think that doesn't come along till chapter 5. So, I don't know if maybe they would.
Oh, you're right. You're absolutely right. So I think what they want you to do is answer the first question based on the data. So let's look at that. So we know that it goes 8.22 meters in 2.8 seconds. And the second time it goes 4.2 meters in 2 seconds. So from these two pieces of data, we can write x, and x0 is 0, equals v0t plus 1/2 a t squared. And there's two equations here. For the first, we get x equals 8.22 meters and t is equal to 2.8 seconds. For the second one, we get 4.2 meters when t is equal to 2 seconds. So we have two equations and two unknowns. What are the two unknowns? V0 and a. Oh, but wait a sec. V0 is not the same in both. Oh, V0 is not the same. No, so this isn't right, is it? Oh, you know what? Well, can we use the equation for V? So 0 is equal to V0 minus AT. Well, that doesn't contain X, does it?
No, but I think you could put the initial into the other kinematic equation.
So you're saying X? You mean this one?
Yeah, that one.
Okay. Well, here, I see what you're saying. So for the first instance, okay, so we have this equation, these two equations for this first instance, plug in t equals 2.8 and x equals 8.22. And we have two equations, two unknowns for V0 and A. So we can solve that for A. Then do the same with these data and get V0 and A. You should get the same A for both of them. I don't like this question. I think it's confusing what they expect you to do. Okay. But the magnitude of the force F versus the total mass M of the box plus its contents. So for all of these data points, we have the total mass. So we have the original plus whatever is added. So we have the total mass. We have the distance M, and we have the time T. This distance in meters. Okay. Now how do we determine the force? Well, we determine the acceleration. So we have this distance, we have the time, which means we have 0 equals V0 plus AT, and we have X equals V0T plus 1/2 AT squared. So for every one of those data points here, we have these two equations and two unknowns. We can determine what A is. Once we determine what A is, well, A equals F over M, or F equals MA. So that's a little F. Okay. That's the first one with that problem.
Okay, I got it.
Yeah. What?
Yeah. It says is the average horizontal force F exerted on the box by the floor the same in each case? That's referring to the friction, right?
That refers to the friction.
Okay.
But the friction, of course, is not the same. The acceleration is the same, but the mass is different. That means the force will be different.
Okay. I got that. All right, I got that.
Okay. If you graph F versus M, what are you going to get? You're going to get A. And it should be a straight line. It should go through the origin, and it should have a slope equal to mu g. Okay. Yeah. that's interesting. We haven't yet discussed friction. Okay, but you can deal with it through the kinematic equations. You don't have to know the model that it's equal to mu times n. All right, other questions?
Oh, actually, I have another question, unless someone else has another question.
You can go ahead, Aurelio.
Okay, so it's 4.46 part B. It's basically making a body diagram with the forces for it. So I thought I did it correctly, but turns out I just can't figure it out. Even though I think I am correct.
Okay.
Yeah, man, give me some guidance on that.
Yeah, let's talk about it.
Okay.
So here's block A. Here's the thick rope. That sounds like a cow in the background. Are you on a farm?
Oh no, that's they're cutting the trees. I mean, the branches.
Oh, okay.
Yeah.
All right. So here's F is given, and it's 200 newtons. You're given mass 1, and you're given mass 2, and you're given the mass of the rope. So, what is the acceleration of the whole system? Is the question you were asking? Is that the one?
No, it's just for the rope.
Oh, just for the rope. So, what is the tension at the top, and what is the tension at the midpoint? Okay, here is what I think is the easiest way to approach this. Treat this as a composite system. And for this composite system, the free body diagram is mg acting downward and the applied force F acting upward. And this M is M1 plus M2 plus MR. That's what this M is. Now you can write F minus mg equals ma, and you can solve immediately for A. Now, once you know A, you can do a free body diagram for each of these three. So what is the free body diagram for M1? The free body diagram for M1 looks like this. We have the force F, we have M1G, and we have the tension at the top of the rope pulling down on it. Now, what about the rope? We have the tension at the top pulling up. Do you notice how these two are an action-reaction pair?
Yes, I did.
Rope acting on M1, and M1 acting on the rope. Okay, you also have M1G acting downward. Oh, now this is for the rope, not M1. I'm sorry. Okay, this is for the rope. So we have the tension, the top, we have the tension at the bottom pulling down, and we have the mass of the rope times G pulling down. And for M2, I have M2G pulling down and the tension at the bottom pulling up. So let's start with this one. T at the bottom of the rope minus M2G equals M2A. It doesn't equal 0. This whole system is accelerating upward presumably. Maybe it's accelerating downward. I'm not sure. But A will be either a positive or a negative number, and that A goes in right there. Now, what about this one? Well, T at the top minus T at the bottom minus mRg equals the mass of the rope times A. But you already know T at the bottom. Now you can calculate T at the top. So T at the top, you've calculated directly. T at the bottom is down here. Since it's linear, at the midpoint of the rope, it's the average. So T at the midpoint is T top plus T bottom over 2, just the average. Now, on a test, I'm not going to ask you something as simple as, what is it in the middle? I'm going to ask you, what is it if this rope has length L? What is the tension 0.25 L from the top? Well, now you're going to have to figure out what the tension is as a function of length along the rope. What you know is that it's linear. So I have the tension as a function of y, where y is the distance from the rope, measured from here. So this is equal to y, is equal to my plus b. Well, if y is equal to 0, then the tension in the rope is just T at the top. So T of y equals my plus the tension at the top. And what is m? Well, m is just rise over run. So m here, by which I mean this thing, that's, you've seen x equal or y equals mx plus b. That's why I used m there. I didn't mean mass. Well, this m is just a rise over the run. So it's going to be T top minus T bottom divided by L. But is it negative or is it positive? Because as L increases, the tension goes down, which means that it's actually a negative slope. So it's actually this, TB minus T top over L. And now you have the equation as a function of y for the tension. Okay, so now you know everything there is to know about this heavy rope. Does that answer your question?
Yes and no. It's just I think the way the actual problem wants you to input it, the answer, it gets very confusing because I pretty much did that. I had the force of the tension of the bottom part of the rope pointing downwards, and then for the top part pointing upwards, and the weight as well downward as another force. I basically did that, and then it also wants you to include the acceleration, which I pointed upwards, but it's still not accepting it. So I think
Oh,
yeah, I don't know.
read me exactly what the question is asking for from Mastering Physics. Can you do that?
Yeah. So it says draw a free body diagram for the 4 kilogram rope. Draw the vectors starting at the black dot. The location, orientation, and relative length of the vectors will be graded.
Oh, okay. Well, then I'm going to go in and I'm going to give you credit on that, because there's no way you can make the relative length of these vectors correct and make Mastering Physics happy.
Yeah, I
Yeah,
tried
no,
to
okay.
get the length more or less correct, but I don't know. It's not.
Yeah, no. You have to use a ruler or something. That's ridiculous. That's a stupid thing in Mastering Physics. Okay. So problem 46.
Yeah, it's actually for A, B, and C.
Okay. 446, give credit. And everything else is clear?
Yeah, except the very last part where you
Read that.
Oh no, the problem itself it's clear, but I guess I was talking about the additional thing you mentioned about how you would present it in the test. I still don't really that.
Okay.
But
Well, let me get some room here.
Professor, for that, is L like a given? Is it like a length?
Yes, it's a length that has to be given. You have to know it,
Okay.
otherwise, you won't be able to. But if it says just in the middle, you don't need to know L because it's the average.
Okay, thank you.
So we have the tension as a function of y. And I would like to know what is the tension right there, 0.25 L from the top. Well, actually, if I give it to you in terms of 0.25 L, the L's will cancel. You don't need to actually know what L is. All right, so the way I've defined it is that this is y equals 0, and this is y equals L. You know it's a straight line. So as y increases, the tension decreases. So it looks like that. Now, what is this? Only it's not from the origin, is it? It looks like that. So what is the equation of this line? Well, it's going to be in the form tension as a function of y is equal to, let's use another symbol for the slope other than m. Let's say the slope is ay plus b, where a and b are constants. Well, it's easy to determine what a and b are, okay? B is the intercept. B is the value when y is equal to 0. So we know that B is just equal to the tension at the top, right there. Now, what is A? A is equal to the change divided by the distance y. Well, the change goes from, let's see, T top to T bottom. So it's T bottom minus T top. So final minus initial, 0 versus y equals L, divided by L. There you go. That's it. And now you know this, you know the intercept and you know the slope.
Okay, that's pretty clear.
Okay, good. All right, other questions?
On the PIP, I think 4D1 was a similar concept. I was wondering if we could go over that.
Yes, we can. For D1, a blimp is initially at rest hovering when at T equals 0, the pilot turns on the engine driving the propeller. Is that the one you meant?
Yeah.
Okay. The engine cannot instantly get the propeller going, but the propeller speeds up steadily. The steadily increasing force between the air and the propeller is given by the equation F equals KT, where K is some constant. If the mass of the blimp is m, find its position as a function of time. Okay, you're ignoring air resistance. Okay, so, well, this is actually this is formally very easy. It sounds confusing, doesn't it? But formally, it's very easy. F equals k times t. But acceleration equals F over m, which equals k over m times t. Now, I know the acceleration, then its position as a function of time is easy, because x, its position, is equal to x0 plus v0t plus 1/2 k over m. Oh, I'm sorry. What am I doing? Okay, what did I start doing that was dumb, everybody? Tell me. Tell me, Andreas, what did I just do that was dumb?
I can't quite find it.
I was assuming constant acceleration, but acceleration is not constant.
Gotcha.
So the whole point of this problem is that we have the acceleration, A is equal to dv dt. Therefore, v as a function of time is equal to v0 plus the integral from 0 to t, k over mt dt. And I should put primes there. However, we know that v0 is 0 because it's not moving initially. So that means v is just equal to 1/2 k over m t squared. Now, what about position? Well, v is equal to dx dt. That means that x as a function of time is equal to x0 plus the integral from 0 to t, v of t prime dt prime. But we know that's 0 because we'll start at the origin. So what is the integral of this? Well, this is 1/6 k over m t cubed. Okay, and that I think is what he's asking for. This, I believe, is what is being asked for. So the whole point is that you know the force as a function of time, therefore you know acceleration as a function of time. Now, develop the kinematics. And it is not correct to say that the acceleration is a constant. Okay, so this formula that I was writing down, x equals x0 plus v0t plus 1/2 a t squared, that doesn't apply because the acceleration is not constant. Instead, these other equations apply.
Okay, thank you.
You're welcome. Okay, other questions? All right. Well, let's see where we are with lecture. So we've completed chapter 4. And we are beginning chapter 5. We've talked about friction. And we did some examples. Let's review the block sliding on the floor.
Professor,
Yes.
sorry to interrupt, but do you mind maybe looking over one more problem?
Sure.
So it would be 4.45.
All right. Boxes A and B are connected to each end. They're connected by a light vertical rope. There's an applied force. Okay. So block A and block B. and there is an upward force which is given, right? 80 newtons. This rope is considered a light rope, not a heavy rope. Now, what other information are we given? We start from rest, and the whole system descends 12 meters in 4 seconds,
Correct.
going down. Well, that means that this force is not enough to overcome gravity, so there's a net force acting downward, and that net force will be a constant force, right? It'll be the gravitational force minus the applied force. So we know the acceleration is a constant. So now we can use our constant acceleration kinematics. And I have delta x equals x0 plus v0t plus 1/2 a t squared. Well, we know that it starts at rest, and I'm going to let its initial position be the origin, so x0 is 0. So my delta x is actually minus 12. So the initial position is 0 right here, x equals 0, and then the whole thing 4 seconds later is at x equals minus 12. So minus 12 equals 1/2 a t squared. I know t. Okay, now I can find a, and I'm going to get a negative value for a. And what do they want to know? Oh, what are the masses of the 2 boxes? Oh, and they tell you the tension here is 36 newtons. Okay, well, now what we have to do, now we know A, okay? So now what we have to do is do some dynamics. Let's do a free body diagram for mass A, the upward force, the tension force, and M1, or MA rather, G. Now for box B, we have the tension force, MBG. So I have 2 equations, force minus tension minus MAG equals M sub A times the acceleration that I got from this equation. And for mass B, T minus MBG equals MBA. Well, I can calculate for MB immediately. Well, actually, I can calculate for MA immediately. MA and MB are the unknowns. They're decoupled. Solve this for MB. Solve this one for MA. That's the problem. Was that the? Does that help?
Yeah, it does. I think I was having issues with the fact that it said the force was applied upwards and then it was moving downwards, but not. But you explained it so that
Okay.
made it clear. Yeah.
Okay. Good. Okay. Excellent. All right. Let's go back to the block that's sliding. Let's say here at x equals 0, t equals 0, I have a speed v0. Then my block comes to a rest here at x equals, let's say, d. All right. So if the box has a mass m, then what is the frictional force? Well, the frictional force is going to be mg times mu. But the acceleration is divided by m, so it's just g times mu. But that's a negative because it's in the negative direction. Okay, now let's write down the kinematic equation. At the end of the motion, V final is equal to 0 equals V0 plus AT. Now, this equation can be solved for t, the time it takes to go from here to here. Now that I know that, I can write d is equal to x0, which is 0, plus v0t, which is known, plus 1/2 a t squared. So all I have to do is take the t from this equation, plug it in, and I'll get the distance d that it travels. Now, when we learn about energy considerations, we're going to find that it's even easier than this to solve this problem. Even easier. Okay. Let's look at a really interesting problem. So we have a floor. And we have a box. There's static friction here. Let's say that it's moving. So let's make it kinetic friction instead for right now. And let's pull on it with an applied force, which I'm going to designate as T, the tension in the cord, but that's the same as the applied force. That's applied at an angle theta with respect to the horizontal. So let's do a free body diagram for the block. We get mg t at this angle theta, and the frictional force, little f, is in this direction, and I left out one of the forces. Christopher, what force did I leave out? Aman, what force did I leave out?
Did you leave the normal force acting on the block out?
Yes. So I left out the normal force here acting on the block. So let's write these equations. Oh, we need another equation for F, but let's do that in a moment. So I have T cosine theta minus the frictional force is equal to, let's say that this block is moving. Now let's say that it's moving with an acceleration a to the right. Now, let's write the equation in the vertical direction. N plus T sine theta minus mg equals, okay, Aman? What do I write here? What is this equal to? No. Is it accelerating vertically? Well, we would write this is acceleration in the x direction right here. So here we'd write m times a in the y direction. But is it accelerating in the y direction or is it attached to the floor? It's attached to the floor. So I'm going to write just a here. So this means the horizontal acceleration, and this is 0. Okay, now what are my unknowns? My unknowns are my tension, the frictional force, the normal force. Oh, no, the tension is known. I'm assuming the tension is known. I need to have something known. So let's assume I know how hard I'm pulling on it. The normal force, friction, and the acceleration are the unknowns. So I've got 3 unknowns and 2 equations. I need another equation. Well, my other equation is my model for F. F is equal to N times mu sub K. Now, this equation can be solved immediately for N, assuming that I know T. N is simply equal to mg minus T sine theta. So the normal force of the floor pushing up on the block is just going to be the weight of the block minus the vertical component of T, because I'm pulling upward on the block slightly, aren't I? If I'm pulling upward on the block, then I'm reducing the normal force between the block and the floor. So I know N, and now I can put that in here, and for F, and I get T cosine theta minus F, which is mg minus T sine theta times mu sub K equals ma. And now I can solve for A. So that's the acceleration of the block. Now let's ask a different question. You can ask lots of questions here. I'm going to just use a different color. So let's say that the tension is just enough to keep the block moving at constant speed. If that's the case, then the acceleration is 0. And my equations in that case become T cosine theta minus F equals 0, and plus T sine theta equals 0, and F equals N times mu sub K. Now, what are my unknowns? Well, the normal force is unknown. F is an unknown. But T is also an unknown. So before I assumed a value of T and asked, what is the acceleration? Now I'm saying, let's assume the acceleration is 0. What is the T that is necessary to keep the block moving at constant speed? Well, now I've got 3 equations and 3 unknowns again. So let's write them as T cosine theta minus F, which is N mu sub K equals 0, and N I made a mistake. Oh, minus mg. I forgot mg. Oh, for heaven's sake. Okay, when I make obvious mistakes like this, you guys got to say something. So minus mg's got to be in there. Okay, So now I have n plus t sine theta minus mg equals 0. So what do we want to solve for? Let's solve for t by eliminating n. So this gives me n equals mg minus t sine theta. So I end up with t cosine theta minus mg minus t sine theta mu sub k equals 0. Now, did I do that right? So what is t? Well, t cosine theta minus mg mu sub k plus t sine theta mu sub k equals 0. So my tension is going to be mg mu sub k divided by cosine theta plus mu. Oh, I don't have room to write anymore. Darn it. Okay, so what is t? T becomes mg mu sub k divided by cosine theta plus mu sub k sine theta. All right. Now, let's ask ourselves, oh, and what is, okay, let's look at limits here. In the limit as theta goes to 0 degrees, what happens? Well, if theta goes to 0 degrees, the sine theta is 0, and the tension is just mg, oh, and cosine theta goes to 1. So the tension just balances the frictional force mg mu sub k. That was easy. What happens when theta goes to 90 degrees? Well, if theta goes to 90 degrees, cosine of 90 degrees is 0. So this becomes, t simply becomes mg. So in other words, I'm pulling straight up like this with t. Now I have a constant acceleration, or a constant velocity, I'm sorry, to the right, but it happens to be 0. Now let's ask a different question. Let's ask a question. What value of theta minimizes the force necessary to get it moving? So now I've got a little bit different situation here. Here I have the block sitting here, and it's at rest, and it has a mu sub s. And let's say it's a mu sub s is the maximum mu sub s. So I've got to overcome the maximum frictional force, which is mg mu sub s. I mean, if I'm not pulling at an angle, it would be the normal force times mu sub s in order to make this move. So let's pull it with a tension T at an angle theta. So what value of theta minimizes the T that I need in order to get this block moving? So you know from your own experience, I have a heavy block on the floor. If I pull up on it a little bit, it's easier to move than if I pull straight. So, however, the greater the angle pulling up, the less the force in the horizontal direction. So the two effects cancel each other partially, and there will be a minimum value of T at a given theta. Okay, so how do we determine what that is? Well, T is equal to, let's go back to the previous solution, which is mg mu sub s max divided by cosine theta plus mu sub s sine theta. And I'm going to write this as mg mu sub s times cosine theta plus mu s sine theta to the minus 1. Now, I want to set dt d theta equals 0. That's going to give me my extreme value of theta. From physical reasoning, I know the extremum is going to be a minimum. So I don't have to do the second derivative test or anything like that. So these constants in the solution of this equation aren't going to matter. So all I have to really do is differentiate this. So what's the derivative here? It's going to be cosine theta plus mu s sine theta to the minus 2 times minus sine theta plus mu s cosine theta. Now, setting this equal to 0 is the same thing as writing minus sine theta plus mu s cosine theta equals 0. Because this is the numerator, this is the denominator. Well, if it's going to equal 0, we need the numerator to be 0. And this tells me that the tangent of theta is equal to mu sub s. So what is the optimal value of theta at which to pull on this thing? Theta equals the arc tangent of mu sub s. Mu sub s max. We almost always mean the max when we write mu sub s. Okay, that was kind of interesting, wasn't it? Does anyone have any questions on this? Let's put our block on an inclined plane. So the plane has an angle theta. I have a block of mass m, and let's go ahead and have the force, the applied force, or the tension in the rope, whatever way you want to call it, parallel to the plane. So what's the trick that I'm going to play here? Alvaro, what's the trick that I'm going to play?
What do you mean by trick? Like,
Well, I'm going to do something. Excuse me. I'm going to do something with the coordinate axes.
don't you make it like kind of? I don't know how to explain it, but like you make the hypotenuse into like the x.
There you go.
Right.
Exactly. Exactly. What I'm going to do is I'm going to rotate the axes so that my x-axis lies along the plane and my y-axis is perpendicular, of course, to x. And these axes become the x-axis and the y-axis. Now, I'm going to do a free body diagram for M, but to make it easy to pick out components, I'm going to superimpose the axis on my free body diagram. So this is X and this is Y. And my forces are what? I have F acting along here. I have the normal force acting here. And I have mg acting downward. But if there were no friction, the incipient motion would be up the plane. So I'm going to draw my F this way, my little f friction force this way. And those are all the forces now. But notice I need to solve for n in order to solve for F. So let's write down the equations here. We have F minus little f minus mg sine theta equals ma. And in the y direction, excuse me, I have n minus mg cosine theta equals 0, because the acceleration is in the x direction, not in the y direction. So, oh, we need one more equation, don't we? I want to know, well, I don't know F, don't know little f, don't know n, don't know a. But let's say that, well, let's just get one more equation and then we'll talk about it. We know that little f is equal to n mu. Now let's ask the question, what is the minimum force necessary to hold this block in place? Then this would be mu sub s max. So we're assuming mu sub x is the max value. Now I'm assuming F is acting in the negative direction. Actually, F is acting in the positive direction, keeping it from sliding down. So I'm going to end up with a negative value for F, but that's okay. So let's say I want to just hold it in place. I let this be 0. So this equation gives me n equals mg cosine theta. This equation gives me F equals mu sub s mg cosine theta. And from this equation, I get big F is going to equal mg sine theta plus us mg cosine theta. Okay. Now, actually, I did something wrong here. So F is acting downward. Since I'm assuming F is in the negative direction, I have to put in a negative sign here because N is a positive number, mu sub S is a positive number, but I've put F as being in the negative direction. So that means I need a minus sign there, which means I get this. Which means I get a negative sign here. It's easier to just have F drawn in the right direction to begin with, given your situation. But it doesn't really matter. If you excuse me for one moment, there's something I have to fix. Okay. So that's going to give me the minimum force necessary to hold this block in place. Let's do a variant of this problem. Now let's put block mass in here, but let's n equal theta, and assume that I have static frictional force mu sub S. Okay. Now, I want to write down the condition such that friction will hold this block in place and then it won't slide. So I'm going to do the same trick. Make this my x-axis and this my y-axis. And now I'm going to do a free body diagram, but I'm going to superimpose on it my coordinate system. Okay, now what are the forces that are acting on this? Well, I have a gravitational force acting straight down. I have normal force acting along y. And in order to keep it from falling down, the incipient motion is downward. Therefore, my friction force must be acting upward. So this becomes mg. This is my friction force F. This is my normal force. So let's write down the equations of motion. In the y direction, I have n minus mg cosine theta equals 0. And in the horizontal direction, I have F minus mg sine theta equals 0. 0. And I have friction is equal to N mu sub S. So let's write these equations again. N equals mg cosine theta. And I have N mu sub S equals mg sine theta. Is that right? So let's just divide the second equation by the first, so I get a tangent instead of a cotangent. And I'll get mu sub S equals, oh, wow, that was easy. Okay, tangent of theta. So given a maximum value of static friction coefficient, the angle, which is the largest angle at which this mass will not slide, is given by theta equals the arc tangent of mu sub S. And this is called the angle of repose. Have you ever gone to the beach and taken a bucket of sand and piled a bucket of sand like this? And then you put more sand on top of it and more sand on top of it. And what you will find is that this angle right here is a constant angle. You can't make that angle any sharper. If you keep trying to put sand on top, the sand will slide down the sides until this angle is achieved again. Why is that? Because this angle is the angle of repose for sand sliding down the sand hill. So sand sliding on itself. Let's say you have here's the ground, and you have a cliff like this. And you've put your house here. Okay, there's your house. Now let's say this cliff face is made up of different layers of soil and that they're down at an angle like this. So these different strata in the soil are like this, such that there you go. That angle is theta. Now, why doesn't this cliff just slide down? Why didn't this whole thing just slide down onto the house? Because theta is less than the angle of repose. But now let's say we have heavy rains. And the friction coefficient, mu s, for this layer is much less when it is wet than when it is dry. Now theta is above the angle of repose. So now what happens? You have a mudslide. And you have all this cliff falls down on top of this house. Okay. There's a place like this in California. It's right along US 101, La Conchita, I think it's called. Has anyone ever been up there or familiar with it? Basically, there are beautiful homes right under the cliff, right along 101. And the homes are beautiful, and they're very inexpensive. Why are they so inexpensive? Because every once in a while, the cliff falls down on them, and you can't get insurance for them. No insurance company will insure them. So you can buy a beautiful house right near the beach, very cheap money, but when the mudslide occurs, that's it. Your house is gone.
That's reassuring.
Well, you know, maybe, I don't know. It doesn't happen all the time. It happens every once in a while. And maybe your house won't be destroyed. Maybe the mudslide will go around you and just destroy your neighbors and you'll be fine. So if you want to take that risk, you can get a nice house cheap. All right, so basically that is friction. There's also rolling friction, and rolling friction is defined exactly the same way as sliding friction. It's not really that interesting. So here's the wheels on the bus. And here's the bus. Oh, I wonder why I got that funny thing. All right, now, you know from experience that although rolling friction is much less than sliding, right? It's easier, you can push this truck because you can make the wheels turn. But if it were sitting on the ground without wheels, you wouldn't be able to push it. There would be way too much friction. So rolling friction is much less usually than static friction, but it's not zero. If the smooth rolling condition, which we will learn about later, and no deformation of the tires of the ground occurred, then rolling friction would be zero. But because we have deformation of the tires in the ground, and you've seen a tire sitting on the ground of a truck, okay, there's a flat spot on the bottom. Okay, that flat spot gives rise to the rolling friction. So what is rolling friction? Well, the rolling force of friction is simply equal to the applied force necessary to make this roll at constant speed divided by the normal force. So the normal force is the total force upward on the truck, which is nothing but the weight of the truck. FA is the force that I need to apply in order to make this move at a constant speed. So FA is just the force that overcomes the rolling friction. So measure that, measure the weight of the truck. Oh, I'm sorry. I said something wrong. This is mu for rolling. So measure FA, measure N, you get mu. And the model is that the frictional force, F friction, is just mu sub R times N. So my rolling friction goes up if I put stuff in the truck and make the truck heavier. And this is just an empirical constant defined just the way it is for sliding friction. So it's really the same exact thing as sliding friction, isn't it? It's not that interesting. Let's take a break. Yeah, let's take a break. And we're ahead in lecture, so let's take a break for half an hour. So get something to eat and drink. I'm going to go have lunch. And what I want you to also do during this half hour is look over problems from PIP and Mastering Physics and be prepared with some questions. So I will see you again at 3:30.